What if there's a planet where gravity doesn't behave the way physics says it should? Not weaker, not stronger, but behaving differently, depending on where you are. Astronomers have discovered real worlds where gravity produces effects no one predicted, and this matters because gravity controls how planets form, how atmospheres survive, and how entire solar systems evolve. By the end of this documentary, you'll understand how one planet forced scientists to rethink how gravity works beyond our solar system, and why it changed the way we search for other worlds. If you enjoy calm, evidence-based explorations of the universe, you may want to stay with this story. Because to understand how gravity can appear to break, we first have to understand why gravity usually works at all. And what scientists discovered next changed everything. Gravity feels familiar. Drop an object and it falls. Planets orbit stars. Moons remain locked in predictable paths. For centuries, gravity seemed simple until Albert Einstein revealed something deeper. Gravity isn't just a force. It's the bending of spacetime itself. Mass curves spacetime. Spacetime guides motion. Under this framework, gravity follows clear rules. More mass creates stronger curvature. Distance weakens its influence. Stable systems remain stable over time. And across our solar system, those rules hold. So when astronomers began discovering planets that didn't follow them, the assumption was simple. The data must be wrong. But as detection improved, through transit measurements, radial velocity data, and atmospheric analysis, the inconsistencies remained. Some planets were too large for their mass. Others retained atmospheres they shouldn't be able to keep. A few existed in orbits that appeared unstable, yet persisted. At first, these seemed like rare exceptions, until one planet stood out, a world so light, so inflated, that its own gravity appeared barely strong enough to hold it together. But it did. And that's when gravity stopped looking so simple. The discovery itself was quiet. A distant star dimmed slightly, a fraction of a percent, as a planet passed in front of it. From that tiny signal, astronomers calculated something astonishing. The planet was enormous in size, but astonishingly low in mass. This type of world is known as a superpuff planet, and it immediately raised questions. Its gravity should be weak. Its atmosphere should escape into space. The structure should collapse over time. And yet, none of that happened. The planet possessed an atmosphere thousands of kilometers thick, far larger than expected, and it remained stable despite intense radiation from its star. When scientists analyzed how particles behaved within that atmosphere, they noticed something strange. Gravity's effects changed with altitude far more than predicted. In some regions, particles behaved as if gravity were stronger. In others, weaker. Not broken, but inconsistent. The planet wasn't violating physics. It was exposing the limits of our models. And the deeper scientists looked, the more unusual the picture became. Because this planet wasn't solid in the way we expect planets to be solid at all. The key wasn't gravity alone. It was the planet's internal structure. Unlike Earth or Jupiter, this world lacked a dense, compact core. Instead, it appeared layered with vast regions of extremely low-density material. This meant mass wasn't distributed evenly. And gravity depends on distribution. In some regions, gravitational pull was concentrated. In others, it was spread thin across enormous volume. Add intense heating from the nearby star, powerful atmospheric circulation, and magnetic interactions, and gravity became just one force among many. Particles didn't simply fall downward. They moved sideways. They rose, cooled, condensed, and sank again. From a distance, gravity looked unreliable. But in reality, it was being balanced by extreme pressure, temperature, and motion. This realization changed everything. Because it meant gravity itself wasn't failing. Our expectations were. For decades, astronomers categorized planets neatly. Rocky planets, gas giants, ice giants. But worlds like this blurred every boundary. They showed that planets can exist in delicate balances far stranger than anything in our solar system. Balanced on the edge of collapse and evaporation, yet stable for billions of years. This forced scientists to revise how they estimate planetary mass, atmospheric survival, and habitability. A planet once dismissed as unstable might be long-lived. A thin atmosphere might be misleading. A low-mass world could still protect itself. These discoveries matter, because when we search for Earth-like planets, we rely on gravity-based assumptions. And those assumptions are now changing. But the most important lesson came next. This planet wasn't rare. Others like it existed. And together, they revealed that gravity doesn't define planets alone, interaction does.